start? Let's start again. So today we're going to talk about local methods. It's a full room again. So is there any reason why everyone just decided to come back for local methods? I didn't scare you enough. So today's going to be quite different. There's not going to be any expected maxima. It's a nervous laugh. And these local methods, we wanted to give to have one lecture on these methods. Of course, one can have a whole course on this. But the reason is that the proofs and the types of results that we're going to get are really different. And if you're in this class just because you want to analyze neural networks and you don't care about anything else, then maybe this can pique your interest. It's not clear whether neural networks should be analyzed as a global method, such as what we've discussed so far, or as a local method, which is what I'm going to do now. So that's kind of something to keep in mind as we go through this lecture. Okay, so let me go again through the kind of the high level picture. I apologize for repeating it in the beginning of every lecture, but it's crucial. So we're interested in the first lecture in this topic. We agreed that this is going to be the object of interest. Right? The expected L of f hat. F hat is our algorithm learned from data, and now in expectation over the data, what can we say about its out of sample loss? Right? That's the object of interest. And we compare it to L of f star, and the meaning of f star changes, as Lorenzo mentioned. It's called the base function, and it's the minimum over all functions in the universe, measurable functions, the minimum of expected loss. So this is the best you can hope for. Okay. Then what we did is we said, all right, if the problem is very simple, such as a perceptron or regression in finite dimensions, then you don't really need to do Biasvariance tradeoff unless you're going for some other aspects of a problem to get the very detailed answer to the like minimax rate. But other than that, you don't need to do Biasvariance tradeoff in those situations. But as soon as you start looking at more interesting problems, there is a Biasvariance tradeoff that you have to, in some sense, you have to put it in, right? You have to come up with a split. You cannot do it all at once. You have to come up with some split such that the two parts are manageable, right? That's the idea. Right? So the Biasvariance tradeoff is not present necessarily right away, but it's something that you put in as a split into two terms or maybe more terms, so that you can analyze the problem. And what we've done so far is we've split it according to f hat minus L of the best in some class f of functions, and that's the estimation error, and then this is the approximation error. And we only talked about the estimation error because for this you need to take courses maybe in function analysis and understand the approximation properties of a class with respect to some other class of functions. Okay, so that's one way to do Biasvariance. What we're doing here is we're saying, I cannot in one go, I cannot just minimize expected loss well based on the data. So I'm gonna only work with a class f, script f, that introduces a bias, because I'm not working with all functions, I'm only working with a constraint class. And therefore I incur a bias and, I incur a variance and a bias. Okay, that's the meaning. So we artificially introduce this class f as these are the only functions I'm going to look at. Okay, and that introduces a bias into the procedure. But then the variance is controlled. You can control the variance, And the variance is controlled exactly by the capacity, right? This term is driven by the capacity of f. How large is f? Okay. Any questions about this? This should be clear at this point. I've repeated this several times. Please ask me if this is not clear. It's a very basic kind of fundamental approach. Now, once you do the split with f, it makes sense to minimize empirical error. Right? It makes sense to minimize empirical error restricted to this class f. And we saw when this is a good procedure. One can also not do the split, but do it implicitly by regularization. So Tikhonov regularization that we've covered so far, where you add lambda times the norm of a function in RKHS, implicitly that puts you in some ball in this RKHF space. So that's your class F now, right? So you can think of it that way. Does that make sense?
So for the first half, you said it's variance. So I just feel like this word is kind of.
Yeah. So.
Yeah.
Yeah.
It's your using expectations.
Yeah. So right, good. So I'm using variance in a very loose sense. That's correct. Better to use the word estimation error. I'm only using it in the sense that the problems in analyzing this term arise because of fluctuations of this empirical process. That's the only reason that I'm using the word variance. Okay. Again, regularization methods are a variant of this. Should I explain this more? Why regularization is effectively like being in a ball in that space? Should I do this quickly? Let's do it. So this is not an aside. So let me just an aside. So suppose that you're minimizing over f in all of RKHS. Let me describe it by h. H is this RKHS space. Sum of f of xi minus yi plus lambda norm of f squared in this RKHS space. Okay, that's the regularized least squares approach, right? In particular, if it's a class of linear functions, you would be minimizing a norm, and this is a lifting into a space where you can treat it as a linear problem, essentially, but infinite dimension. Okay, now let me call this objective. I don't know. Give me a letter. A. Okay, this is the A objective. So this is A of f. Well, then, if f hat is argmin of this, right? Then I claim that its norm cannot be too large. So why is that? Well, I know that A of f hat, by definition, is smaller than, or no larger than A of a zero function. Okay? A zero function. Just because I searched over the whole space, this is a Hilbert space, it contains a zero function, right? But what is the value of A at 0? Oh, I forgot the square, sorry. Well, it's a 1 over n sum of yi squared, right? Yeah? How about the left-hand side? Well, that's some non-negative fit to data of that f hat plus its norm, lambda times its norm. So lambda times the norm is bounded by that, right? So effectively, you can think of the norm of f hat being bounded by something like 1 over lambda times something. Now, this something depends on the data, but I'm just giving you like a very rough hand-wavy argument that the effective radius is like 1 over square root of lambda. So even though we didn't really restrict anything here, we said do it over the whole space, but regularize. That's very similar to restricting to a ball of radius 1 over square root of lambda. Right? There are some caveats here because this constant depends on the data. It's a random quantity, and so morally this is the idea. Okay, so that's just an aside. Any questions about this? Yeah. What?
GI.
Oh, this is just yi. Sorry. yi squared. Yep.
Is it trivial to assume that norm of zero function would be zero in that space? Like you could have a complicated function which will give you a zero function, but like the only zero function available.
But I will take also the zero. You were saying that the zero function is not in the. No, it has to be in the space, right? Because
no, I'm saying it has to be in the space, but is it true that its norm has to be zero?
I think so, because I take the one that puts zero for every coefficient in the expansion, and the norm is the sum of the squares of these weights.
But like you're assuming linear in this case? Like
it's RKHS, yes. Yeah, it's a reproducing kernel Hilbert space. Okay? Okay, so that's one way to do Biasvariance, really. I'm pretty sure that you can come up with your own Biasvariance trade-off, but let me give you one that is being used in statistics, and that's the one that we're going to use for KeyNearest Neighbors and the other I will. Okay, so from now on, I will work with a square loss. So L of f of x minus y, or sorry, comma y is just the f of x minus y squared for the rest of this lecture. Let me rewrite our goal, right? This is the star is our goal. So you have expectation over the data set. That's S, right? I'm not writing it, but our convention is that if I don't write the random variables over which I'm integrating, then it's everything that's random, right? I have to integrate everything out. That's our convention. So, but let me be explicit. So I'm integrating over S. By the way, in the notes, this calligraphic S comes out in the like this, like in the slides. Kind of looks nice, but if you don't like it, you have to hack the PDF, I guess. I don't know. Okay, so expected S. And now expected over a new pair xy of f hat of x minus y squared. That's just the definition of the first term, minus, so star is equal to, minus, and we know that the minimizer of this is expected f star of x minus y squared. Again, this is just over x and y. Okay, where f star is the regression function, right? This was from the first homework, right? F star is equal to eta, which is so f star of x is same as eta of x. Sometimes we use eta. That's the regression function, expected value of y given that x is equal to x. Right? Okay. So, the first thing that I'm going to do, I'm going to continue this equality. I'm going to write this as expectation, again over S and over xy of f hat of x minus f star of x plus f star of x minus y squared minus expected f star of x minus y squared. Okay, I just added and subtracted f star of x. Nothing changed. But now I'm gonna write this as a, a plus b squared is equal to a squared plus b squared plus 2ab. When I do that, the b squared is going to cancel with this term. Yeah? Now, what's going to happen to the cross term? So it's this guy times this guy. Now, I claim that it's in expectation it's 0. Why is that? So first condition on the x, and just look at the expectation over y. When you condition on the x, this part is fixed. And now it's just a y variable that's oscillating around f star. But f star is the mean of that variable, so that becomes 0, right? No? And now there is no y variable anymore, so I'm going to write f hat of x minus f star of x. So I'm doing an expectation over, I'm averaging over the data set, because remember the hat is the whole data set. And that of course has x's and the y's. But now I have to just take expectation over x. There is no y variable anymore. Yeah? Let me just to write out this integral. It's an expectation over the data set. And then what is the expectation over x? Let me just write it out for you. It's the integral over the x variable, right? That lives in some space, Rd, of f hat of x, I'm now writing it as a little x, minus f star of x, this is just the dummy variable, squared, p dx. Okay, that's just the definition. Right? Any questions about this? It's just the definition of the expectation. Now, this is actually an object, f hat of x minus f star of x. That object, that difference, is in the purview of statistics, not parametric estimation. Right? Remember the first lecture, right before perceptron, someone was asking, why don't you do, I think you were asking, right? Why don't you do a function minus a function in some norm, right, squared, or a parameter minus the parameter of the distribution, distance squared, right? Now this is a notion of a distance, right? It's essentially looking at a function f hat that you produced and f star, and it's looking at square differences, right? So you look at the difference as you range over the x variable, you square the difference, right? And then you take the average over all the x's under the measure of the x's. Yeah? Make sense? So sometimes this is called the integrated risk. So you can if you exchange this integral and this expectation, this would be a risk at a certain point, right? So you can say for a given x, and that's what we're going to do. For a given x, can you estimate well? Can you make sure that f hat of this particular x is close to the true regression function value? And then when you average over the x's, that's called the integrated risk. Right? So what we're going to do is often we're going to swap these and just study for a particular x what happens. And then if we get a result, it's just the integration of that result over the x. That's going to be the final answer. So often if we get a number, so let's write it as integral over the x expected s of f hat of x. this is a fixed x now, minus f star of x squared p dx. Okay, so this is you can think of this as a risk, and this is the integrated risk. Okay, so if we get a bound on the risk for a particular point, and that bound does not depend on the point, then we also get the bound on the integrated risk, right? So sometimes our results will depend on whether x is at the boundary of a set, because things get weird at the boundary, and then you have to distinguish whether this x is so not all x are the same in some sense, right? Okay. So let's study. Here, everything is equality, right? And maybe you remember in one of the early lectures I said there is a point. Well, I guess it was the first lecture. I said there is a point where what we studied, the prediction problem with square loss, is equivalent to the problem of estimation studied in statistics and nonparametric regression. That's it, right? We rewrote it with equality. So the problem of prediction with square loss is exactly equivalent to the problem of estimating the regression function. I will sometimes work with this guy and sometimes work with this guy. Let me also say that you can view this as a sort of a norm. So this object highlight. So this object can be written as a norm between f hat and f star. It's some notion of a distance, right? And we call it L2 with respect to P. Which is exactly that. Okay? All right. So, the story now is exactly the same as before. We would like to estimate this function f star, assuming that it's only, let's say, Lipschitz. So we're going to assume that f star is Lipschitz. So the regression function doesn't do crazy things, right? Which means that, let's say, if you're thinking of let's say, classification problem, you have cats and dogs plus minus 1. The Lipschitz means that cats don't quickly become dogs, right? In a certain sense. You don't like you shouldn't quickly by moving in the space of pixel values. You shouldn't very quickly come from a cat to a dog. It's an assumption. It will make things easier for us. Okay. Okay, but the issue is the same. If I want to estimate this f star, I cannot do it in one go. Okay, it's exactly the same problem because there's going to be too much uncertainty about what the data actually tells me. So I have to introduce Biasvariance, but I can't just split it according to some f, right? That would be like what we did before. So I'm going to do something else now. So I'm going to use that norm notation. I don't know if you can see it. Just because it's a shorthand that makes things a bit easier. And I'm going to drop the L2P so it becomes a bit more compact. So what we have is the object of interest, the star, is equal to expected over the data set norm of f hat minus f star, right? That's our object of interest. Yeah? So as before, remember I added and subtracted L of f sub f. I'm going to add and subtract something else. But what I'm going to add and subtract depends on my estimator, or it depends on my f hat. So what I'm going to do is I'm going to add and subtract the following quantity. So equality, I'm going to look at f hat minus the expected f hat, and then plus expected f hat minus f star. Okay? And that will give me a bias variance decomposition. Now, there are two things you can do. You can ask, what is this expected f hat? This expectation can be over the data set. But what I'm going to do now is I'm just going to take the expectation over the y variables in the data set. So you've got your data set, x's and the y's. I'm only going to take expectation with respect to the y variables, okay? So this is expectation over y1 through n. Again, y1 through n. So what's the meaning of this? What is the picture? So I've got this true regression function. This is my f star. It gives me noisy values. If it's a classification problem, 0, 1, let's say, they would always come like this, right? 0, 1, the y values. But it doesn't matter. Let me just think of an arbitrary y value, which is real value. So I get values like this, right? Okay, so there's some, this is like say x1, and I get this value, which is y1, and so forth, right? I get noisy values of the function. So what this expectation says is, take your procedure and look at its output. So I have in mind some procedure that estimates this curve. Let's say it produces this curve. Okay, that's the output of my learning algorithm. Yeah? But if I had given that algorithm the same x's but different y's, it would be something else, right? So what this expectation is the average of all those green functions when I have fixed x values, but randomized over the y values. Is that clear? Any questions?
So you are still taking the expectation over training data?
Yes. 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 So there are several expectations here. So let's think about this. This is the expectation over the training data. X's and the y's. And this is the random variable that depends on all of them. This random variable, this is the algorithm that needs input, right? So it will take the x's from the data set, but its y values that are fed into that algorithm are averaged over. Right?
What's distribution function?
Everything is this. So once I tell you that xy has distribution p, you know everything. Right? So it's expectation over the y's drawn from that data set, conditionally on the x's. Right? Is the meaning of this clear? Yes.
Just to clarify, if we go back to the images of the cats and dogs, for example, the idea is that one photo, right, represents some x's that sometimes we would label that as a cat and sometimes as a dog.
Exactly. Right. So x's now are fixed, and I'm asking, what is the mean output of your function if someone else would label this data set, let's say? Yes.
So if
if you're considering the binary classification
Yeah.
problem, then this expectation might not be binary.
That's right. The mean function is not binary. But right. But I don't have to output the binary valid function for classification. I'm thinking of actually estimating the mean function, the regression function. Yes.
In the definition of the norm, there was this integral over all x.
Yes.
And then here you have also expectation.
It's hidden here. It's hidden.
So when we're talking about the expectation over yi's and the x is fixed, which x exactly?
Okay. So let me write this as expected s, and now I write it as an integral. Yeah, the nice thing about shorthands is that they make it look nice, but then you're hiding, right? So okay, good. So what I'm doing is I'm looking at f hat of little x minus expected f hat, which itself is a function of x1 through xn and y1 through yn. So let me integrate over y1 through yn. Plus same thing, of x, right, of x. F hat, f x, y1 through n, minus f star x squared p x. There. Okay. So this decomposition is with respect to the method. So you fix a method such as KeyNearest Neighbors, which we're going to analyze in a second. I'm going to look at the expected output of the procedure as a function for the fixed x's, but as I draw y's, right, from that distribution. Okay, so let me go on. I'm going to, as before, I'm going to open up the square as a plus b squared. A squared plus b squared, and then the claim is that the cross term in expectation is 0 again. Why is that? So it's this, the cross term is this times that. Now, condition on the x's here, when I integrate over the y's here, this one is 0 mean, because this is the mean of that over the y variable, right? So the cross term is 0. Okay? You know, sit down in the privacy of your home and try to work it out. It's very basic conditional probability. And so if you're familiar with conditional probability, you should be able to deduce that the cross term is 0. Okay, so now, again, I'm going to collapse this notation, but f hat minus selected f hat squared, again, this is just y1 through n, plus expected over the data set of expected f hat as a function minus f star. Okay? In fact, this is only over the x variable. There is no y variable anymore. Right? So I can just replace this with the x1 through n. Okay? Yes? Okay, so it's this times that. This term depends only on the x variable. Okay, so maybe I said it in the reverse, right? Sorry, I apologize. Sorry, thanks for asking. So this term depends on both x's and the y's. This term depends only on the x's. I'm going to claim that this term makes the product 0. Okay, so why? This is the mean of this random variable when I take expectation over the y. Now look at this product and condition on the x's. Then this is a constant conditionally on the x's, and this one is a 0 mean as I average over the y, right? Sorry, thanks for asking. This is variance, and this is the bias. And the meaning is, or I should say maybe bias squared, and it depends what you call exactly the bias. But the idea is that maybe you want to call this the bias. It's like saying, as I average over the outputs of my algorithm with respect to the y variables, do I even get close to f star? Like, is my algorithm even able to get close to f star or not? And that has the same meaning as before when I restrict my algorithm to play in script f. It's a don't step outside of f, because if you step outside of f, I cannot control the stochastics, right? It's the same thing here. Given that I restrict myself to this algorithm, these are the stochastics. That's the variance term. And this is the bias, right? How badly I'm doing just because I restricted myself to be this algorithm, right? Make sense? Questions? Okay, so let's analyze. Let's analyze. Okay, we got the first one. Let's analyze KeyNearest Neighbors. Then we're gonna do Nadaraya Watson, and then we'll talk about interpolation. Okay. So KeyNearest Neighbors. So again, we've got data x1, y1 up to xn, yn, IID from p as before. By the way, I'm writing this p and this p has the same letter. This should be the marginal of the x instead of the full xy, but okay, you understand. So let me first describe the idea of local methods. So what local methods will do is they will say, I've got f star, which locally doesn't jump too much, right? So it's like Lipschitz, let's say. So if I need to predict at a point, what I'm going to do is I'm going to look at neighbors around me, points that are close, because their values should be representative of my y value, right? That's the whole rationale. So it's a local method. If you need to predict at this particular x, at this image, let's say, you're going to look at who is like this image in some notion of, let's say, distance. And then you say, oh, majority are cats. Or if it's real valid predictions, then you just average locally the y values. And you output that as a y value. Okay. That's the idea of the local method. Now, contrast this with a global method, where you minimize empirical risk over a class of functions. You can't make, well, sometimes you can, but in general, you cannot make these guarantees that you're really pulling together local information. Because the minimizer of your empirical risk could have some weird things going on just because that's the class of functions. There is no reason a priori, unless you can specify exactly what this class of function should look like, how it should match the regression function. There's no reason why it has this local behavior, okay? All right, so KeyNearest Neighbor is the first one that comes to mind. So you order, given little x, so now we're gonna do conditionally on x. I need to tell you what f hat of x is, right, to define my output of the algorithm. And that's gonna be the same x that is gonna be used here. And again, I can write out these norm squared as the integral over x, and that's the x that I'm going to consider. So given x, I order, I'm going to write 1, y1, x, and yn according, let's say, Euclidean distance minus x. Okay? So this is the closest x to my little x. This is the second closest up to the furthest element in my data set. Okay? Now, for the rest of the lecture, I'm going to hand wave. Because I want to get across the kind of the behavior of these objects, but I don't want to get bogged down with the details, which are you can go and read. So if I have to define f hat at a little x, I'm going to define it as 1 over k sum over y I from 1 to k, right? So what is k? K is a parameter. That's KeyNearest Neighbors. So you take the average of, let's say, 20 images that look like your image, right? That's KeyNearest Neighbors. And all I'm saying is sort the data and look at the y variables of the closest points and just average them. Does that make sense? Yes? Okay. The feature of these local methods is that you have to produce f hat that has some parameter. That's going to be true for all the methods we consider. You take a method f hat, an algorithm that has some tunable parameter. And typically it's going to be the case that this guy either increases or decreases, and this guy goes in the opposite direction. And so there is some optimal setting of the parameter. And in practice, you cross-validate that parameter. Such as KeyNearest Neighbors, you choose the optimal k. Let's proceed. Okay, so let's look at the. So this is my procedure, right? So let me look at the. Let me look at the analysis. And I'm going to put it in quotes because I'm going to hand wave. Okay, so what is expected with respect to the y values, 1 through n, f hat of x? So x is fixed. x1 through xn are fixed. And I'm just looking at, as you draw the y values from that distribution conditionally on the x, what would be the average output of my k-nearest neighbor rule? Well, let's look at this, right? You take expectation, just by definition. The nice thing about these methods is you specify f hat typically in a closed form, and so you can just work with the formula in that closed form. So that's just going to be 1 over k sum of f star, right? Because the f star is the mean of the y variable at xi. Right? That is the average value of y given x. Yes?
I didn't get why you get from expecting to x star to that. So I can say y is expecting of yi.
So you take expectation of this.
Yeah.
Expectation of the average is the average of expectations.
Yeah.
So you just have to take expectation of the y variable. The expectation of y variable is exactly the f star value by definition. It's the regression function, right? Yes?
So this implicitly implies that f star is able to explain all of my data. Like it's the best function.
It is the best function. What's important here is that f star is the f star at any x is the mean value of the y given that particular x. So think of it, what's the average value of a cat-dog label 0, 1 for that particular image? Well, maybe it's 0.99 because it's unlikely that someone would label this cat as a dog. Okay. So we're analyzing the variance part. So then yi minus, sorry, then the f hat at x so I want let's see. That's equal to 1 over k sum of yi minus the expected half of x is equal to, this is just over the y variable again, this is equal to 1 over k sum of yi minus f star of xi. Right? 1 over k. From I from 1 to k. Okay. So that's the that's this part for a particular x. Now I have to square it, right? So if I write this out, this is a expectation over data integral of f hat of x minus expected f hat of x squared, right? So now I have to square it. So when I square and I look at the expectation over the x variable by swapping the integral and the expectation, it's just the variance of this random variable, right? So what is the variance of the average of k zero mean random variables? If I have 1 over k sum of zero mean random variables, the variance goes down as k. So it's 1 over k, right? Standard deviation is 1 over square root of k. Variance is 1 over k. So this term, now I hand wave the first. A little bit, but not too much. This is actually, so the variance is order of 1 over k. Okay, that was easy. Let's look at the bias. So bias requires a bit more work. But not too much. So what is the bias? The bias is, let's look at this difference. And using that formula, so the bias is 1 over k sum of f star of xi minus the f star of little x, right? And this is going to be the feature of these local methods. Whenever you have to talk about the bias, you think about the noiseless case, where y's are not noisy at all, right? So suppose that you knew the f star, the regression value, at your points. The only randomness is from the x's. and you average the f star values, will you get close to the true value at the x? Right? That's the only randomness, right? So the picture is I've got my f star, and for the bias, I don't care about the y values. I'm going to draw a bunch of x values, x1, xn. And now I have to predict at a certain point x. And suppose someone actually tells me the f star values for my nearest neighbors. So it's this value, and that value, and that value. These are my 4 nearest neighbors. I'm going to average these the f star values, and I'm going to predict that at the new point. So is that close? Well, it depends how far these x's are, right? If these x's are very far, all I know is the function is Lipschitz. So I really need to make sure that these x's are close. When is that going to happen? I have only n points in d-dimensional space. I need to make sure that they start filling up the space. And that's a feature of non-parametric methods. They will only work if you've got enough data locally. If you don't have enough data locally, that's not good enough, right?
I have a question about the bias
Yes.
formula. The first term is f star xi, and the second term is f star x.
Yes.
Yeah, I
So the little x is that from this x, right?
Yeah, but here you write f hat, so I didn't see why the f hat goes to f star.
Because of, I just wrote it here.
Oh,
So now the idea is to bound the variance is to say, if I take k large enough, I'm going to have enough points around me. But not too many, because I don't want to average far away points. I just want to average like close by points. And because the function is Lipschitz, they're going to tell me something about my true value f star. Again, I have to square this, right? So I have to square it. Now, by Jensen inequality, this is upper bounded by 1 over k sum I from 1 to k, I from 1 to k of f star of x in the ordered list. Sorry, f star. But the function is Lipschitz. Let's say 1 Lipschitz. So this difference is bounded by the distance between points squared. 1 over k sum of the norm between x I minus x squared. Okay. So the quality, my bias is going to get worse and worse if my points are far away. Makes sense. Yeah, so there's a Lipschitz constant, I'm going to say 1. I'm going to skip a lot of details. Yes.
A question, why instead of the number of the points around one point, you don't restrict the distance that the points around each point have?
Yeah, so I'm going to say KeyNearest neighbor.
No, instead of that, you just fix the distance that point has.
You could do that, yes. Yes. So you could say, let me look at everyone in the radius r from me. And that's the node that I lost in that one. Yeah, so I'm going to get there. Yes?
Why isn't it 1 over k squared?
Oh, yes. No. No. So I'm using using Jensen, which says that square of average is upper bounded by average of the square. So you can put the average outside. Yes?
So we use the fact that we are close to x for the bias term, or did we also use it for the variance?
We did not use it for the variance, no. Not here. Yeah, you see, variance only used.
Use somehow that they are ordered.
No, I'm just using the fact that these are zero mean random variables. Yeah, yeah. So
For some, like, let's say.
for some actually, the nice thing about this KeyNearest neighbor is that it's really distribution free result. It will not require an assumption about the distribution as long as dimension is larger than or equal to 3. In dimension 1 and 2, you need conditions about the distribution a little bit, slight distribution. I can give you references. In dimension 3 and higher, you have the following result. So dimension 3 and higher. So I'm not going to prove it. Let's just take it as a given. Dimension at least 3. The expected distance between a random point x drawn from some distribution and its closest among n points is at most up to constant, let me say this. What? Anyone wants to guess? So you draw n points, and then you draw one more. Everything is random. What's the expected distance from a random point to its closest? I think Shiyu knows the answer, but he's sleeping. Yes? You need a little bit of assumptions. This is no assumptions at all. Oh, assumption of compact support on the x. So compact and compact x. So it's a bounded set. Okay? So I'm not going to prove it. The claim is that this is enough to finish KeyNearest Neighbors in 1 minute. Okay. Here's a trick, which is very cute. So you've got data points x1 up to xn in the unordered list. So this is the original. Think of it as the random variables. I'm now gonna make blocks, and just suppose that n divided by k is an integer, let's say j. Okay? Let's suppose it's an integer. So I'm going to make k blocks, 1 up to k blocks, of size n over k each. Right? Now I need to understand the average distance squared from the k closest points to my point x. Yes? Now this is at most the average distance of the closest in each block to me. So I replaced KeyNearest Neighbors, which could be anywhere in this set, by the closest from the first one, the closest from the second block, the closest from the kth block, right? But I know the behavior of the closest point, and that's it. So in expectation, when I take expected over both the x variable and over my data of the 1 over k sum of xi minus this x squared, right? So this little x now is I'm taking now expectation over it because it's an integral over the little x, right? So I'm drawing both x and the data, and this is upper bounded by the closest from these logs, and that has it, and that behaves as so what's this? How many? I have n over k to the power minus 2 over d. Okay, up to constants. Right. Clear? I'm just asking in each block, what is the expected distance to the closest point? It's this. But now I don't have n points anymore. I have n over k points. So that's the closest. That's it. So we put together the star. Remember that was the excess loss. That's what we wanted to prove. Then we decomposed it into a bias and variance. That's upper bounded by the variance term was 1 over k, and the bias term was k over n to the power 2 over d. And now if you balance it, you're going to get n to the minus 2 over 2 plus d with the appropriate choice of k. Okay, so k has to be n to the 2 over 2 plus d. Okay, so the optimal setting in KeyNearest Neighbors, the optimal setting according to this theory, optimal setting of the KeyNearest Neighbors to aggregate is n to the 2 over 2 plus d, and what you get is sample complexity, which is called non-parametric because it becomes pretty slow in large dimensions. This is called the non-parametric rate. Okay? Yes. Yes, I think so. Yeah. Maybe Shuya knows more. It's good enough for a government work. So I waved my hands, but I hope you got the sense of how these two terms behave. There's always in this bias variance trade-off, there is always a parameter that you choose. One term bias goes up, or the other way around goes down. You optimize, you get the result. Okay? So this approach is completely different from. We didn't use any empirical process theory. There was no expected maximum, nothing, right? It was more like define a method, look at its expected behavior, decompose into bias variance, and you've got the result, right? Okay. And so maybe, I don't know, maybe neural networks can be analyzed by looking at the expected output of the neural network. Of course, you have no idea how the training goes, so all bets are off. But it's not clear that neural networks, right? The neural networks are piecewise linear functions, right? Where you take ReLU, and they have lots of pieces, right? And they try to fit the data. And so maybe you should be studying them as a non-parametric estimation procedure. Yes?
So for the variance, you have O of 1 over k, but here it is sample. Do you care about the?
Yeah, I skipped so many little details that's not even. There are lots of details that I skipped. So if you want a rigorous proof, look at Georfi book et al. It's called the Distribution-Free Theory of Non-Parametric Regression. I put reference in the slides. Okay, good. Daraya Watson. We got KeyNearest Neighbors, Daraya Watson. We're not gonna order the data, but we're gonna do what's suggested here is to say, I'm not gonna look beyond a certain radius. I'm just gonna aggregate things around me. Or you can say something more smooth. I'm gonna give weight to everyone. It's a democracy, but I'm gonna discount whoever is far away from me. So my estimator F hat, so this is not that I have Watson. Watson. This estimator was introduced by Parson. Maybe you've heard of Parson Windows. Parson Windows is the density estimation version of this, but it's very close. So it's gonna be a vote among all the y values. Everyone gets to vote, but everyone is gonna get discounted by a weight wi, which depends on the particular x. I can write down that dependence. Yeah, let me write down the dependence. So what is the weight? The weight is going to be some notion of a distance. I'm going to describe what this is. X minus xi divided by, just normalize it. X minus, so let's make it little x. X minus xi. I'm going to put a parameter. It's not going to be k anymore. It's going to be called h. H is here. I'm going to subscript it with h. H is going to be the bandwidth. I'm going to define this k function, the kernel, in 2 steps. First, I'm going to define k of x to be something like, let's see, example. K of x is equal to 1 minus the norm of x to some power. Let's see what I have. I don't know, let's say this, and then take a positive part. So it looks like that. At 0, it's 1. At x is equal to 1, it becomes 0. So it looks like a hat, okay, or minus 1. Or it could be a Gaussian that looks like that, but then what the analysis I will present doesn't quite work for the Gaussian. Let me just cut it. Okay. I can also present. I can also use the just a box from -1 to 1. That's fine. Just a box. Or you can put a triangle, something of that sort. Right? I'm going to require that it's not too slim. So within that, you can find another rectangle of some constant size, because averaging has to happen. Averaging is going to happen from that bulk. So these are the weights. It's just a way to normalize the weights. But I haven't defined kh. So kh of x is just k of x over h. So if this distance is further away than h, so if xi is further than h from little x, then this is more than the argument here is more than 1, and so it drops to 0, right? So this averaging only happens. I said democracy. I lied, like we do nowadays. We're only going to average a particular x, which are within radius h, and we're going to choose that h in a particular way, right? But if you take the Gaussian, everything will go through. That's going to be democracy. Just you're going to downweight those farther away. Okay. So you do exactly the same thing. You look at the bias and the variance. But here, the bias actually is simple. So I'm going to analyze that first. And the variance requires a bit more work, and I'm just going to hand wave. So let's see, the bias. So first, I'm going to look at the expected f hat at the point x with respect to the y1 through n. Okay, so you take the expectation with respect to the y variables. So this yi becomes what? As before? F star, right? Becomes F star. So it's a F star of x weighted by xi. xi weighted by wi of x. So now if I subtract off the F star, I'm just subtracting off the F star of x here. But now, because this is a convex combination, right? These weights add up to 1, and they're positive. Right, so there are a couple of assumptions on k that I'm sweeping under the rug. So k is positive. K squared is integrable. I'm going to assume that k squared integrates. So integral of k squared is finite. This is equal to the sum I from 1 to n of f star of xi minus f star x wi of x. Now, the story is very similar now to the bias term in the previous case. We have to use smoothness property of f star, right? It's not about the noise in the y variable. It's about if I knew the f star at the xi's that I've got, can I reconstruct the x, right? And I'm going to use the fact that the weights are 0 outside of h radius. So I'm going to continue that. I'm going to claim that, let me rewrite this. The sum of f of xi star minus f star of x weighted by the weights x. Right? Again, it's a convex combination. These are positive. I'm going to use the Lipschitz property, so this is upper bounded by Lipschitz constant times, I'm skipping all these steps, minus x times wi of x. Yeah? I'm using Lipschitzness. Of f. Because w's are positive. And I know that all these weights are 0 if this distance is more than h. So this is bounded by h. That was easy. That's all. That's the bias. Variance is more difficult. And I'm just going to tell you the result. You can read it up, you can read in the notes. It's not important. Well, let me just say that the variance can be estimated to be 1 over n h to the power d. Okay? So now we balance the bias and variance, or bias squared. I forgot to put square. It depends what you call the bias. Do you call the bias like the squared thing or a non-squared thing? So let me say bias squared plus variance is h squared, right? Because we need to square this term. We need to square it. So that's h squared plus 1 over n h to the d. And if you choose h correctly, so if h is n to the minus 1 over 2 plus d, that's the radius of points that you're going to be averaging. Then this is n to the minus 2 over 2 plus d. It's the same thing we achieved with the other method. There are many things I swept under the rug because you need to be worrying about the boundary, what happens at the boundary, because you don't always get enough points if you're at the boundary, because if you're at the boundary, you have a small number of points that are close to you in that radius ball and so forth. But morally, this is the idea. Okay, I want to spend the last 5 minutes on something that I'm going to talk about in the ML seminar next week on Wednesdays. I'm giving a seminar like 4:30 maybe, something like that. A machine learning seminar. I'll talk about interpolation. And I want to spend the next 5 minutes talking about interpolation. So, if I take this kernel, to be something like that, let me erase this. Let me take the kernel that looks something like so. First of all, it will have enough mass here to average things, right? That's the meaning of that bulk. It's averaging the y values close to your point. But now I'm gonna make it high. I'm gonna go like this. And let's make it like a kappa. Or okay, let me tau. Let's make it tau. Right? So one example is if I define a kernel at x to be 1 over the norm of x to some power alpha, but then I cap it. So I take a minimum with tau. Okay, so it explodes at 0, right? 1 over 0 explodes, but then I cap it. Okay, so it would be like that. So by varying tau, I better and better fit the data. So let's see if you believe this statement. What happens to these weights as x approaches to any data point xi? So as x approaches xi, this distance goes to 0. So the kernel blows up, and so this becomes the only weight that matters. And so you're averaging only the yi that belongs to this xi. In particular, if you just let the kernel go to infinity, you will interpolate the data. Now, nothing in our proof breaks down. The proof is the same. But now it's a weird situation because we have a method that interpolates the data, but it's okay. Right? Now, this is the final kind of the final point I would like to make. H here is the parameter, and it's still there, right? Because that H controls the kind of the width of this, how much we're averaging. If you look at books on machine learning or statistics, you typically have the following picture. You have bias variance. So you have some parameter, bias variance, or model complexity, I should say. So this picture is called bias variance. Bias variance trade-off. And you have some model complexity. Model complex scheme. And you have this U shape, typically. Yeah? How many of you have seen the bias variance shape like that? Okay, many. In particular, if you look at Statistical Learning by Hayes-Tibshirani from Stanford, they also plot the empirical fit to data. So this is the training error. And typically what is said in the way that we teach machine learning or statistics is if you fit the data too well, then you've overfit. And so you must be in this regime. And therefore you must be in this regime where there is too much variance. Now what we saw is that you can interpolate the data, and that tau parameter is independent of the age that you choose. In particular, you can be optimal in terms of the bias variance and decide how well you're going to fit the data. So now the question is, what is overfitting? Who can tell me what is overfitting? What's the meaning of overfitting? Yes?
This isn't guaranteed with generalization gap.
The word overfitting is used in two ways. One is you're doing very well on the data, but you're doing horribly out of sample. The other way that overfitting is being used is your model is too complex, so the variance is too large, then it's overfitted. But you see, I just produced to you a situation where you can fit the data as well as you want, and there is a bias variance trade-off, and you can still do, in fact, optimally in this case. You have a learning procedure that has guaranteed good out-of-sample performance with respect to square loss. So in some sense, the values of the loss on the training data are not necessarily any indication of whether you'll overfit, which kind of puts a strange spin on the neural network discussion, the narrative, where people say the models are too rich, we fit the data very well, but we still predict well, so something is off, right? And there are many things we've been discussing why this is problematic. A statement like that is problematic. And here is one more example. I can give you an example where you fit the data exactly. You go through the data points, right? If you've got data like this, you would be going through the data points. You're optimal with respect to the L2 squared loss. So what is overfitting? You cannot deduce overfitting from data. You cannot look and say, I have very good fit to my training data, therefore I overfit. Right? And actually, I mean, to be frank, I don't know what the word overfitting even means. I don't know what it is. I'm sorry. I mean, I understand you can be on this side, so the model is too complex in terms of this parameter. That's well defined. But that has nothing to do with how you fit the data. And so I'll give a whole hour on this at the machine learning seminar. If you're welcome to come, and you have all the background you need for that. Any other questions? Yes. So that's okay. 1 over x squared integrated.
Also,